Hey, what's
Hey,
going on, Mr. Wing? What's going on? How you doing?
oh, I'm doing great. How about yourself?
I'm all right. Good to see you again, man.
We got a good one here for you. Strengths of acids and bases in Ka and Kb. This one's going to be one of the epic videos. I just know it.
It's gonna be epic. It's gonna be huge. This is one of the longer ones, right?
Yeah,
Of the remaining three, they only have three, Mr. Wing. There are this is the longest of the three, but it's gonna go back to that equilibrium we learned. It's like literally going to hit home on that one. So we're gonna use some ice tables and get ourselves rolling. So let's not dilly dally, Mr. Wing. Let's get started, okay?
okay.
All right, man. Okay, so why don't you go over this and tell us what is a strong acid base? Do you have to memorize this crap?
They used to,
It does say it says
not this
memorize.
time. So anyway, strong acids, they're listed there. You're supposed to memorize them, but I'm assuming you're not going to because you have access to this. Hydrochloric acid, bromic acid, iodic acid, nitric acid, all those things are strong. Um, and they're strong because they dissociate. And we're going to talk about that on the next slide.
Yeah.
Uh,
Look at these three. These are all the halogens, aren't they?
yeah,
What
yeah,
halogen's not
yeah.
listed though?
Fluoride.
Fluorides, right? That's the one that's not included in those strong acids. So any other halogen with hydrogen is going to be a strong acid, but not fluorine. And when you get into college chemistry, I'll teach you more about that. But then you had to memorize these guys: nitric, sulfuric, and perchloric acid, right? All right. What about bases? What makes them strong?
So, so we have group one, which is the alkali metals plus a hydroxide. So remember, with a base, we learned that it has to have a hydroxide with it. So there's an example on the bottom there, sodium hydroxide.
Woo.
Sodium is a group one, an alkali metal, and then group two. Some group twos, not all of them, but calcium hydroxide is a good example of one that you'll see often.
Yeah, I think almost all of them are strong. Like all group two hydroxides are strong, but in order for the base to be a strong base, it has to dissolve completely in water. And I think a lot of the hydroxides, if you go back to your solubility chart, they're not completely soluble in water. So some of them are just not that soluble. So if you can't get them dissolved in water, they can't be a strong base. Uh, but if it's in there, it's a strong one. All right. Great roll.
Let's go.
All right. Let's talk about these strong versus weak acids. Why is hydrochloric a strong acid, and why is acetic acid? What's acetic acid again? What's the common name for it? What's the
Vinegar.
vinegar? I thought I stumped you for a second.
No,
So why?
I didn't know if you're talking to me. I was just
I'm just talking to the world, man. That's all I'm doing. So let's say this vinegar. Why is it I can pour vinegar on my arm and it just hurts in my like open wounds? I don't know why I got open wounds in my arm, but that does that. But if I pour hydrochloric acid on my arm, it eats my skin away. What's the difference? Well, it has to do with dissociation. When hydrochloric acid, which actually is called hydrogen chloride, when we dissolve it in water, 100% of it will actually react with the water and dissociate into hydronium ions and chloride ions. Okay, so this is the part that really like eats your face off right there. Is that hydronium ion, and 100% of hydrochloric acid will dissociate into that right there. Vinegar, on the other hand, only 0.4% of it will actually form products. So it goes back to what we talked about with equilibrium, Mr. Wing, that this one lies heavily with the products will have a large KEQ, and this
yes.
one lies heavily with the reactants, which has a very small KEQ, right?
Yep.
So if it doesn't dissociate, it's just the nature of them, and it has to do with the bonding between this hydrogen here and the other parts of the molecule of how easy it is to dissociate that and donate that hydrogen to water. More on that if you want to when you're older. You're not ready yet. All right, let's go on and talk about the Ka, Mr. Wayne. Go ahead and talk about
Okay.
this.
So we learned first about KEQ, which was the equilibrium constant, and then we actually learned about KW for water. But anyway, we're going to learn about Ka. So A stands for acid. This is the acid dissociation constant, and we're going to do it the exact same way that we learned how to do KEQ, except for we're going to be dealing specifically with acids. And so the formula is the same.
Do we include this water in the Ka?
No, we only include same rule applies. You only include aqueous solutions and gases, so that water is not going to be involved. So
Okay,
uh, we are going to
fascinating.
X that. And so here is our formula. And so notice that the hydronium ion and chlorine ion are on top. The products always go on top, and then the reactants go on bottom. So again, they're aqueous solutions
Nice.
and gases.
So we know that these are aqueous because they have a positive and negative charge. Any ions we're going to assume are in aqueous solution. So we're always going to include anything that's got a positive and negative charge. And we're always going to assume that the initial acid is also going to be an aqueous. So we can put that in there. Is that cool?
Yep.
Beautiful. All right.
But
Now in a strong acid, if this is 100%, like almost 100% of it dissociates into products at equilibrium, there's not going to be much of this left, right? So this amount at equilibrium is going to be really close to zero. And what's that going to do to this number right here? If this number is big and this number is very, very small,
it's going to be huge.
it's going to be huge, huge. Okay. So that's kind of what's going on there. So anything that's got a very large Ka is a very strong acid. All right. Let's go to a weak acid there, homie. Oh, hello. Huge for strong acids. Okay.
Okay.
Here's a
So
weak acid.
the weak acid, we're going to look at how this becomes a really, really small number because look, only 0.4% of it's going to dissociate. So when we write our formula, again, we're not going to include the water. You'll see that we still have most of our reactants because only 0.4% turns. So that's going to make the top really, really small.
Yeah. It makes
And
this one
so
almost the same as what it was
it's
when we.
almost the same. So mathematically, that makes our Ka really, really, really small.
Yeah. So the weaker the acid, the smaller the Ka. The stronger the acid, the larger the Ka. That's pretty simple to remember, right?
Yep.
All right.
I'd write that in my notes.
I would too. I would totally write my notes. Okay. And let's look at for bases. What about bases? Is it any different than acids?
Totally. No, I'm just kidding.
We're
Completely the same idea, same concept.
not going to include the water, right? Products over reactants, nothing crazy. What's the Kb expression? Ooh, Kb expression. So it's the base dissociation constant when a base gets dissolved in water. And we do this same thing. Here's your products: NH4 plus, OH minus over the concentration of the reactant. Don't include water, right?
Now, Mr. Worth, remember, so we'll actually have concentrations of these things, like when we solve for Kb. Like these will actually have real numbers. Right now, we're just kind of showing you like the framework of the formula. But once we get into practice problems, we're going to be putting numbers in there.
Yeah. So like a lot of times the textbooks will say expression. And when they say expression, that means you're not really putting in numbers. You're just setting up what the formula looks like. So that's why they call it an expression. I don't know why they call it an expression, but that's what they mean when they say expression. It means don't use numbers, just set up the formula of what it looks like, and then we'll actually solve for it here in a little bit, actually. What about this pKa and pKb? That looks familiar, right? That little p?
Yeah. So I think in the last video we learned about pH and pOH. So now that we know the Ka, we can also find the pKa by just taking the negative log base 10 of the concentration of Ka. So you have to find the concentration of Ka first. That's that 1.8 times 10 negative fifth. Once we have that information, then we can find the pKa.
Right. It's not a concentration. It's just a number. I don't know what it is, but it's not a concentration.
Oh, right. But
Yeah.
then
But you just take negative log of this, right?
that's it.
All right. So let's see what it'll look like if we took the negative log base 10 of the Ka, which gives the pKa. I have it so memorized. 4.74, right? So that is vinegar. So vinegar is HC2H3O2. The pK of vinegar is 4.74. That cool?
Pretty impressive you did that in your head, Mr. Worth.
Yeah, I know. I always remember that. I memorized it from doing it so many times when I used to teach AP Chem. And then I also remember, I think 474 is the molar mass of alum. So many stupid things floating around in my head, Mr. Wing. It's ridiculous. All right. So anyway, sometimes you're going to have to use the pKa, the pKb, or follow it down. Now, how does this relate to acid strength? Well, just like pH as it gets lower, it means the more acidic the solution is. As the pKa gets lower, the stronger the acid. So a small pKa means the acid is very, very small, and a large pKa means that the acid is very weak. Cool.
Notice where our acetic acid is there, 4.74 is right in the middle.
Right there, yeah. So like if we were looking at hydrochloric acid, it would be very, very small, like probably 0. I don't even know if it can be negative or not. I have to look that up. But it would be like pretty daggone small. Because I think like hydrochloric acid dissociates so much, it's almost like its Ka is like 1,000,000 or 1,000,000,000 or something like that. So I don't know what the negative log base 10 of 1,000,000,000 is, but it's probably pretty small. Okay.
All right.
Anyway, as long as we know that relationship, we are good to go. Okay, we got 3 problems to go through here, right?
Yes, we
And
do.
I know you're excited, Mr. Wing. So.
Yes, I am.
So I'll read the question, then I want you to kind of explain what's going on here. So we have 0.3 molar of a weak acid. Notice it's just HA. That's the generalized formula for an acid is just a hydrogen with some sort of anion. That's why it's HA. And you can use this for anything in this class, just this right here. It was found to have an H3O plus of 1 times 10 to the negative fourth at equilibrium after being dissolved in water. What we want to know is what is the Ka and the pKa of this acid. All right, so first thing we know, Mr. Wang, is what is the formula for the dissociation of acid. And there it is. Okay, there's your HA. What's it going to do? It's going to donate a hydrogen to that water, right?
Yep.
Give me the H3O plus, and then the A minus is left behind, right?
Yes.
So as long as we know that, we can develop what we call the ice table, right? You love that. So I'll bring up the ice table. You walk us through it of what we're doing and why it works that way.
Yeah, I just want to point out also, like this formula will be the same for any acid that we're looking at
in this class.
In this class,
right?
So always start off by writing Ha plus water. Okay.
Man, yeah. And let's see. So you're always going to do the ice table here, and we'll teach you some tricks and tips on how to solve this thing as well, right?
Yep. Remember that we talked before that the initial values, we're always going to start with our products as 0 in this class. So those are pretty easy to fill in when you get this table. And I see that the problem told us that we initially had 0.3 molar of a weak acid. So that's my initial column at this point would be completely full. So that's good. And then we know it's a weak acid. So now we got to figure out how much they change and what the actual equilibrium is. So the problem says that the hydronium concentration was 1 times 10 to the fourth. So that is our bottom right box, I guess.
Bottom. It's actually it's the H3O plus. Hold on, my mouse is frozen. There it is, right there. That's what they have at equilibrium, right?
Yes.
But we know since this has got a coefficient of 1, this has got a coefficient of 1, they're the same, right?
Yep. And we know that since they started with 0, that they're going to gain 10 to the negative fourth because the coefficients are 1. Similar to the reactant, Ha is going to lose 10 to the negative fourth because it has a coefficient of 1.
And if I take 0.30 and subtract off 0.0004, is it going to change that initial amount very much?
It is not going to change it very much. So because we are only going to 2 sig figs, it won't change it at all based on our sig figs. So that is actually going to be the exact same as it was initially.
That's a big hint, isn't it, Mr. Wing?
What's that?
That's a big hint. For this class, we're probably going to always have the same amount of our very weak acid. We're going to have the same amount at equilibrium as we did initially because we just don't form that much product. Right?
So now we have we have our concentrations at equilibrium. We can go ahead and set up our Ka. Notice the products go on top and the reactants go on bottom. So hopefully you're using your E button when you put this in your calculator. If not, you need to put in parentheses. But anyway, you should get 3 times 10 to the negative eighth for the Ka.
I want to make sure that they understand that this is the same. 1 times 10 to the negative fourth is the same as 10 to the negative fourth. They're the same thing, okay?
Yes.
And then how do we find the pKa? If we know the Ka, now we've already solved that part. How do we find the pKa?
So remember that P in your brain, that PED means negative log base 10. So we're going to take the negative log base 10 of 3 times 10 to the 8th, or 3e to the negative 8th. And that gave us a pKa of 7.5.
7.5. And remember, acetic acid was what, 4.74?
So this is even weaker than acetic acid.
There you go. Look at that. That's a great point to bring up, Mr. Wingman. This is weaker than acetic acid because pKa is higher than acetic acid. Nice work, brother. All right, that's one type of problem. The next one is exactly the same. Do you have anything to say about that before we move on?
No.
All right. The next one's exactly the same, except instead of giving us the H3O plus at equilibrium, they're going to tell us what the pH is at equilibrium. And the reason why I like this one is because it's kind of a more of a real life problem. Because if I dissolve an acid in water, the way I'm going to check its acidity level is by putting a pH meter in it. And then I'll know its pH is 5. I can't put a pH meter in something that gives me the hydronium ion concentration. I have to do the math to that. So this is what we're going to do. We're going to essentially take this pH and find the math. So once again, we got a weak acid. Ha! I know how you like that. It's mixed with water. What's the pKa? So we're just trying to find the pKa of this, exact same as the last problem. So let's go ahead and set up the ice table here.
Notice the formula is the exact same that we had before. And our products, again, are zeros. Mm-hmm. Our Ha is 0.15 because that's what it told us. And we gave them the equilibrium already. How in the world, Mr. Worth, did we get this 10 to the negative 5?
So here's the pH here of 5. So what we know is that the pH is 5, and we learned, I think it was the last lecture, that how to get the hydronium ion concentration from pH was to take 10 to the negative pH. So 10 to the negative 5th is the hydronium ion concentration. And once we know the hydronium ion concentration, Mr. Wing, we know the concentration of A minus as well. Look at that guy.
That button.
10 to the negative button. 10 to the, it's just 10 to the button. You have to put negative pH. And the only way we can get from 0 to 10 to the negative 5th is by adding 10 to the negative 5th. What do you got there?
I got 1 to the negative 5th.
There you go. So 1e to the negative 5th is the same thing as 10 to the negative 5th, right? Nice work.
Okay.
So the only way we can get from 0 to 10 to the negative 5th is to add 10 to the negative 5th. And we know since these are 1s and this is a 1, we had to subtract the same amount that we added here. And guess what? 0.15 minus 0.00005 is probably not going to change at 0.15.
Pretty close to 0.15. So you can kind of go ahead and fill those in before you even get the problem started. But now that we know the concentrations, we can put in our Ka formula. Again, 10 to the negative 5, 10 to the negative 5 divided by 0.15, just like we did last time. 7 e to the negative 10th.
I bet this is a weak one. You ready? Oh, pK is about 9. So of the 3 that we've had, this is the weakest of all of them, isn't it?
Yes.
I think, what was the last one? Was it 7?
7 point something, I think.
Yeah, so we had 9 here, we had 7, and then the acetic acid was about 4.7. So this is the weakest of all the acids that we've dealt with, right?
Yep, and that's how you find it, folks.
That's beautiful. So
we
got one more, which is a little bit tougher, just a different way. And there's definitely a one like this on the test, and I actually worded it exactly like it is on the test. We got benzoic acid, which this is not the formula for benzoic acid. Look at this.
There's your answer.
Don't look at that, everyone. So we have 0.25 molar of benzoic acid, which is HA, was found to have a pK of 4.0. Okay, so we now know the pK. Remember on the last one, we were trying to find the pK, right? What it wants to know is what is essentially the pH or the H3O plus of this acid at equilibrium. And just like before, since it's such a small Ka, which you're like, is it small? It is. We can assume the initial concentration of the acid is the same at equilibrium as it was initially. Just like we did here. See, initially it's the same as it was at equilibrium, right? And that was for both of them. So here we go. We're going to set our ice table. Mr. Wing, you ready? You excited?
Yep. But it's essentially, we're just going to have to work a little bit backwards for this one.
Yeah.
So that it's not that it's that much more challenging. It's just we have to kind of do our steps in reverse order than we did the first two.
All right. So we know we start out with 0.25, and we know we start out with 0 and 0, right?
Yep.
But we know that these products, since they have 0, we know the equilibrium is going to shift and make more products. So we know we're going to make more products and we're going to lose some reactants, right? But we also know that the amount that we're going to lose is not going to be any more than what the initially was, because it's such a small amount we're going to lose. It's going to be the same here. But we know that if we start with 0 and we're going to add a certain amount X, we know that we are going to have X at equilibrium, okay? So we got to figure this out. So we got to remember it's Ka equals products over reactants. But look at our Ka. They gave us the pKa of 4. But how do we find the Ka if we're given the pKa? We take
10 to the negative fourth.
10 to the negative pKa, right? We got
Yep.
that. So now what we're going to do is we're going to basically multiply both sides by 0.25 and then take the square root of them, and you'll get your X. But remember, X is equal to the concentration of H3O plus at equilibrium, which is 0.005 right there. And if that's our H3O plus, if we take the negative log of that H3O plus, we end up getting 2.3 as our pKa, or pH. Sorry, not pH. So if I had this benzoic acid and I had a 0.25 molar of it and I dissolved it in water, right? That was the molarity. And I stuck a pH meter in there, that pH should be around 2.3, which remember below 7 is acidic. So that's still pretty acidic, right?
Pretty acidic for sure.
Yeah, and look, this is stronger than acetic acid, right?
Yep. And that's like similar to your stomach acid. Stomach acid, I think, is like a 2. So
Yeah.
that's breaking down all the junk all the McDonald's that you eat.
Delicious. I think that's it, Mr. Wing. Hey, look at this meme I found. It's pretty good. You get it? Look, new password acetic acid, and they said weak. And then new password hydrochloric acid, said strong. It's a good one, huh?
That's awesome.
All right.
All right. We'll see.
I think that's it. I guess I'll see you tomorrow, Mr. Wing.
Okay.
Tomorrow's is very, very short, I think. I think we just go over salt hydrolysis. It's kind of an awesome deal.
It's going to be amazing.
All right. I'll see you later, man.
Bye.
Bye.